calculate the distance between a point and a line in space. Not only will we calculate this distance, but we will also derive its formula. The distance between a point Q out in the space and a line here, where on the line there's some point P that we can distinguish, and then the direction vector for U, a vector on the line, is given. So then we should be able to calculate here this distance between the point Q and the line. Now, how do we do it? Well, it's very straightforward. It comes from the idea of the parallelogram, in that we recall that we can use that parallelogram to our advantage. Let's see. I want to take this example, or this illustration, see if we can paint it over here. So we have some angle theta. This is the point P. The point Q is here. So this is the line segment, and its length is the line segment, the norm of PQ. And down below is this vector U with magnitude or length, the norm of U. If you take this to be h, the height, then we can calculate something. We know here that sine theta is equal to the opposite over, and I need to illustrate this h in better detail than what I'm doing, divided by the hypotenuse, the norm of PQ. Here, this h, I'm looking for its length, so that's the norm. So, if this be the case, and it should be to reason that this h is the height, which is a length. So I don't want to have all these symbols. It's somewhat cumbersome. Just write h. I think we're okay with that. So this implies that h is equal to this norm of PQ times this sine theta. Right? Well, actually, what I'm calculating, or trying to calculate, is that distance, h, which is what I want. But there's something that we recall from before, that if I take this cross product, the cross product gives me the area of this parallelogram. So here, this comes out to be the norm of the cross product of PQ with U. So if that be the case, then I want to be able to use this in the formula for calculating the height. But do you recall that the area is also the base? Oh no. I'm really messing up now. You hit a button, and nothing works right. Just, sheesh. The area is the base times the height. So the area, which is here, this norm of PQ cross product with U is equal to here the base, which is the norm for U, and then the height, and the height is this norm of PQ times sine theta, right? So that looks familiar. But sine theta times this norm of PQ is the distance. So what we have is that the norm of the cross product, can't get my Q's right. Q sine phi is equal to the norm of U times this distance. That's what I'm looking for, right? That's that height. So the distance then is this cross product divided by the norm of U. I believe that's what we sought out to find and to show and to prove that this formula is congenial. It's the proof that D is actually the norm of the cross product of PQ and U divided by the norm of U. Well, if that be the case, then we can use this formula to actually compute a problem. Here in this exercise, it says find the distance between the point and the line given by the set of parametric equations. And so we use the formula that the distance is the norm of the cross product of PQ and U divided by the norm of U. What is U? U would be the distance, the direction vector. Here, which is the A, B, and the C. So for this problem, that gives us 4, 0, and -1. Remember the equation of the plane, the equation of the line that represents the plane is x equal to, this is AT plus x naught. This is y is equal to BT plus y naught, and z is equal to CT plus z naught. And so this is the point Q. So Q is sitting up top do my drawing again. is Q. This is the line. The line L, that's represented. Here Q is 1, 5, -2. This is the point P. P is a point on the line. What's a point on the line? Well, take the initial point. -2, 3, and then 1. Right? It's the X naught, Y naught, and Z naught. So then the line is given by X equal to 4t minus 2, Y is equal to 3, and Z is equal to -t plus 1. So we need PQ for this formula. So we go to 1 minus a -2 is 1 plus 2 is 3. 5 minus 3 is 2, and then -2 minus 1, -3. We have U again. We have U. It's 4, 0, -1. We need its norm. So the norm of U, the square root of the 4 squared, 16, plus 0 squared, 0, plus the -1 squared. So we get the square root of 17. Now we need the cross product of PQ with U. We had that formula from the last section, so this is the determinant of I, J, and K. These two bar lines denote determinant, so PQ is 3, 2, -3, and U is 4, 0, -1. Delete the ith row and column, so we get -2. For J, delete the jth row and column, so we get -3 plus 12. -3 minus a -12 is -3 plus 12. So we get 9. And then for K, delete the kth row and column, so we get 0 minus 8, -8. So this is -2. -2i minus 9j minus 8k. Now you got to find its norm. So the norm, the cross product of PQ and U, is the square root of that -2 squared, but I write everything in there, plus -9 squared plus -8 squared. So that gives us 4 plus 81 plus 64. And you work that out on your calculator. And that gives us the square root of 149. So the distance is the norm of the cross product of PQ and U, and that's divided by the norm of U. So this is the square root of 149 divided by the square root of 17. And we rationalize, so we get the square root of 17 times 149 all over 17. That gives us the square root of 2,553 all over 17. 2,533 over 17. I think I wrote it right, but I said something else. Because I'm getting weary, it's time to go home. Thank you. I think that's it.